Welcome back to Gradient Daily. Today, we are looking at Tencent's newly published architecture, HunyuanWorld 1.0. Generating virtual environments requires solving a paradox. Modern 2D video models generate incredibly diverse, photorealistic scenes, but they are flat. They lack underlying spatial data, meaning any camera movement is an illusion. There is no consistent geometry holding the scene together. On the other side of the problem, 3D generative models produce strictly mathematically sound objects. The physics are absolutely perfect, but they fail when asked to generate complex, multi-object environments, because the AI training data for entire annotated 3D scenes does not exist at scale. Bridging this data gap shifts AI from generating pixels to generating actual engine-ready infrastructure. Instead of outputting a flat video file, an AI could export a raw, standardized 3D mesh that drops directly into a physics engine, Unreal Engine, or spatial computing hardware like the Apple Vision Pro. Tencent solved this by combining the strengths of both systems. They used abundant 2D panoramic images as an intermediary proxy, then applied a novel layered depth mapping technique to extract a physically consistent 3D world. The first step in this architecture is the Panorama DIT. While native 3D scene data is scarce, 2D panoramic photography is abundant. By training a diffusion model to output large panoramas, the system captures full 360-degree environmental data from a single generation. Flattening a globe onto a 2D plane creates severe mathematical stretching at the poles. Tencent solves this with elevation-aware augmentation, shifting the horizon line during training to teach actual geometry. To fix lateral seams, circular denoising seamlessly stitches data across boundaries. These steps yield a perfect, unbroken 360-degree image. However, a panorama only allows a user to rotate their head. It is mathematically flat. Before pushing that flat image into 3D space, the underlying model requires pristine training data. Tencent sourced this data from commercial acquisitions, open data downloads, and custom scenes rendered directly in Unreal Engine. This data is pushed through an aggressive filtration pipeline. Automated systems discard inputs for obvious geometric distortion or low resolution. Then, expert annotators manually inspect the remaining samples, throwing out unrepresentative narrow spaces or anatomical anomalies. This curation protocol restricts the volume of training data, but it guarantees high signal quality. The DIT learns exact spatial relationships without inheriting the geometric hallucinations common in unfiltered image sets. To allow a user to actually step soulward in a virtual environment, the system must decouple the objects in the scene from the environment behind them. This is achieved through layer decomposition. Similar to a theatrical stage or a classic multi-plane camera setup, separating the painted background from the physical foreground props creates an explorable parallax effect. An AI agent manages this in 3 steps. Step 1 is instance recognition. The system applies circular padding to the panorama and runs an object detector called grounding dyno. This maps the location of every distinct object, even if an item spans the panoramic seam. Step 2 is layer decomposition. A segmentation model called ZIM draws precise pixel masks over detected objects, physically extracting them into a dedicated foreground layer. Step 3 completes the environment. Removing a foreground object leaves a hole in the background. The system uses a fine-tuned DIT to auto-regressively paint the occluded terrain, guessing the exact lighting and texture needed to seal the gap. By cleanly isolating these semantic layers, the system converts a single static viewpoint into a modular environment ready for spatial computing. With the layers separated, the system calculates the depth of every pixel to push the 2D images out into the z-axis. This introduces a strict mathematical constraint. If the depth of the foreground and the depth of the completed background are estimated independently, they will clash. Objects will float above the terrain or clip directly through it. To solve this, HunyuanWorld uses cross-layer depth alignment. It generates a master depth map from the original panorama, locks the depth coordinates of the foreground objects, and forces the background layer to mathematically conform to those anchor points. This diagram illustrates the world sheet grid mesh mechanism. The system overlays a dense wireframe grid onto the image. Based on the calculated grayscale depth map, it pushes and pulls vertices along the z-axis, warping the flat image into a topographic 3D structure. Sheet warping efficiently builds the macrostructural skeleton of the world. However, it only extrudes the visible face of an object. Because sheet warping relies on a single viewpoint, it cannot render the backside of objects. If a user walks around a warped tree, it will disappear into a flat plane. To make the world truly interactive, the architecture replaces these 2.5D foreground instances with perfectly enclosed 3D meshes generated by the Hunyuan 3D pipeline. The math here relies on signed distance fields, or SDFs. Instead of plotting polygons directly, the system maps a continuous 3D field of distances to a hypothetical surface. The boundary where that distance value is 0 dictates the solid outer shell of the object. An autoencoder called ShapeFay learns this geometry by compressing over 100,000 watertight models. It uses a hybrid sampling strategy, applying uniform points across the surface to capture bulk volume, while concentrating important sampling on sharp edges to preserve detail. A flow-matching diffusion transformer predicts the object tokens from the cropped 2D image, while a secondary model, Hunyuan 3D Paint, synthesizes the physically based rendering textures, specifically albedo, metallic, and roughness maps. Generating hundreds of high-fidelity meshes inside a single scene creates a severe memory bottleneck. The system applies X-Atlas-based UV parameterization to bake the textures, compressing the total file size by 80% without introducing rendering seams. By injecting these fully optimized, multi-sided models back into the warped terrain layers, the pipeline outputs a massive, explorable scene populated with engine-ready assets. The empirical results demonstrate that HunyuanWorld 1.0 sharply outperforms baseline generation methods in both geometric detail preservation and aesthetic coherence across long-range exploration. Prior state-of-the-art methods like Trellis or Layer Pano 3D relied on Gaussian splatting, rendering points of light in a volume. By outputting a rigid, standardized polygon mesh, Hunyuan allows creators to assign physical hitboxes, making the output immediately viable for game development and physics simulations. The architecture does have constraints. The autoregressive layer completion model occasionally fails when predicting highly complex, densely occluded backgrounds. Furthermore, the entire 3D extraction pipeline is inherently bottlenecked by the resolution and quality of the initial 2D panorama. The next logical step for this research is physics integration. If reinforcement learning is applied to the diffusion transformer, future iterations could generate meshes with mathematically accurate mass and weight distributions already assigned to them. Here is the 30-second summary. First, using panoramic proxies bridges the gap between 2D diversity and 3D geometry. Second, agentic semantic layering creates true explorable depth. Third, integrating Hunyuan 3D guarantees the final output is populated with physics-ready, enclosed meshes. That's the breakdown for HunyuanWorld 1.0. For more daily, rigorous analysis of the latest AI research papers, like and subscribe to Gradient Daily. We'll see you in the next paper.